Okay, Aspen Plus, tutorial number 4, part 2. In this part, what we're doing is basically replicating what we did last week in part 1. However, instead of using 2 heat exchangers like we did, so what we did last week is we presented a heat exchanger using 2 heater models, one for the cold stream, one for the hot stream. We did some analysis to maintain the delta T minimum to be 10, and we determined some parameters. So in this tutorial, or the second part of this tutorial, we'll be using the HeatX model. And the HeatX model has some advantages to modeling a heat exchanger. Primarily, you can build in this delta T minimum directly. You don't really need to run an analysis to get it. And it allows you to model a heat exchanger accurately and correctly without having any thermodynamic issues. Because if you recall, when we used the 2 heater models the first time we ran it, we had a crossover and it wasn't able to detect it because they're 2 separate entities. However, now we're using one model and it will be able to see it and report it if there's an issue. Okay, so let's move on to the Aspen Plus file we had last time. Let's see. So it's this guy, and you remember this, we were left off last time. We did our design spec, we calculated our parameters, etc. So what we're going to do is so on the same sheet, I mean, you can use a different sheet, it's up to you. I'm going to drop the HeatX model here. And again, you need to press escape to avoid the sticky Aspen thing with Aspen, or sticky, cursor thing with Aspen. And I'm going to add stream, and you can see this is the cold stream. So the streams going across are the cold streams, and then the streams from bottom to top are the hot streams. And if you recall, in this case, or from last week, basically the cold stream was the water because it's what we're using for cooling. So I'm going to give it the same name. So let's call this H2O N2, just for part 2. And I'll call this guy H2O out 2 as well. And then, if you remember, I think we're using butanol, right? Or let's call it BOH N2. And then we have, leaving here from the top, is BOH out 2. Okay, so this is the system we'll be working on, and let's call this HeatX, which is the model name. And we'll run some analysis using this this model to try and just get comfortable with it and see what it's capable of, etc. Okay, so let's go back to the tutorial, see what they're asking really. What problems do you have, or what questions do you have to answer, and take it from there. Okay, let's go back. See your flow sheet now. Okay, specify the hot and cold stream inlet conditions like we did in part 1. Start with 600 kilograms per hour as the flow rate of cooling water. Okay, so you want to specify them similar to what we did in part 1. So let's just recall what were the conditions here. So for part 1, we had 117.7. Let me write this down. 117.7 Celsius, 2 bars, 1,000 kilograms per hour for the butanol going in. And for the water going in, it was 25 Celsius and 2 bars. Double check, I'm sharing the screen. Okay, it's 25 Celsius, 2 bars, and 600 kilograms per hour. Okay, so let's specify these parameters. So I'm going to close out of these tabs. Okay, let's specify the water in. So we're specifying it in an identical way to part 1. So we set 25 Celsius here, 2 bars, and the mass flow rate of 600 kilograms. Always be careful you're selecting the correct basis, whether it's the flow rate or for the composition. 600 kilograms per hour, and then here we have a fraction, and we want this to be completely water. So set the water fraction to 1. Okay, so there's water. Let's do the butanol here. And we said it's 117.7 Celsius. It's 2 bars or 2 bar and 1,000 kilograms per hour. So again, the flow rate, it's a mass basis and it's 1,000 kilograms per hour. And the composition of this guy, it's only butanol, so the mass fraction or the mole fraction is 1. Okay, so we specified our 2 streams, our 2 inlet streams. Now let's specify what's going on inside this heat exchanger. And if you go to the tutorial, they show you exactly what you need to pick. So I'm just going to replicate what's shown there. We don't need to really redo it or move back and forth. Okay, so we want to use the shortcut method using counter current flow. The calculation mode is design. And again, if you really want to look into different options, you can look in the manual, and different options will allow you to do different things. And as you use it a bunch of times, it's usually a good idea to play around with it, see what the different options give you. Okay, exchange specifications, we're specifying the hot stream outlet temperature. Hot stream, hot stream, oh, first one. Hot stream outlet temperature, you want to specify to 40 Celsius. And the minimum temperature approach is basically the delta T minimum, or the minimum driving force you're maintaining, and it's 10. This case is 10. 10 Kelvin, 10 Celsius, both are the same, okay, so we have everything specified here. Let's go back to the tutorial and double check. So now we need to run the simulation, and we should get an error. Okay, so let's verify this. So let's run a simulation here and see if we get this error like the tutorial says. Okay, so your simulation is completed with errors, that's fine. The following unit operation blocks were completed with errors. Let's go have a look. And temperature crossover detected, recalculating with minimum approach temperature. So the thing about this module is that it automatically detects that there is a violation, that you're going to have a temperature crossover. And once it detects this, it does not complete the calculation as you wanted. However, it recalculates it using the delta T minimum. Okay, so this is an important thing to note. Because if we go back to what we specified, actually, we specified our hot stream outlet temperature to be 40 degrees Celsius. Having it as 40 degrees Celsius will create a crossover with the water, because the water will exit at a temperature higher than 40. So the outlet stream or the outlet hot stream cannot be at 40. So this model automatically detects it. When we did this last week using the 2 heaters, it wasn't able to detect it. It just calculated it normally, even with temperature crossover. However, with this model, it's able to detect it. It will tell you, you know what, you have a violation here, you have temperature crossover. So it actually recalculated the temperature using the delta T minimum of 10. So if I have a look at the results, and I'm looking at heat X, let's look at the stream results. Let's see what it calculated here. Okay, so if you have a look here at the temperatures, we're interested in the temperatures. Let's change them to Celsius. You'll see that it actually maintained, so the hot stream in and the cold stream out, it kept it at, it kept the temperature between them, or delta T between them, at 10. Okay, and this is really the benefit of this type of model. It will automatically detect these types of issues, and if there's an issue, it will recalculate based on the delta T minimum to avoid having a violation. So if you have a big process and you're modeling it, you're always better off using this heat X model. In some cases, you can use two heaters if you have a lot of conversions issues or you're very comfortable really looking at these scenarios and verifying all the calculations. However, if it's not the main focus, you should always use the heat X model to avoid having any sort of thermodynamic violations in your simulation. Okay, so question number 4 is asking, what's the heat duty of the heat exchanger in kilowatt? Okay, so in order to get the heat duty, click on summary here. Again, on the left-hand side, under the tree of the heat X, which is a block we have. And let's see if the results are here. No heat duty results here. Let's have a look at the thermal results. Yeah, there we go. It's under thermal results. And the heat duty for this exchanger is 59.75 kilowatts. And this is very similar to what we got last week, if you remember. And yeah, so this answers question number 4, and we're just practicing with the heat X model. So feel free to, make some changes and get to know this model. Let's go back to the tutorial. The heat X model contains a great feature and allows you to see where the temperature crossover occurs in our original heat exchanger. Okay, to do this, we override the minimum temperature approach constraint by running the simulation with the allow temperature crossover options in the conversions tab, okay? And then after this, we're gonna plot temperature versus heat duty diagram and see where the temperature crossover occurs. So this model will also allow you to see the exact point at which temperature crossover occurs. And in order to see it, let me close out of all these tabs. Okay, we're gonna open the block setup page, just double click on it. And then under conversions, look here. Where is it? It's in the options. So under the options here, conversions tab, and we want to select allow temperature crossover. And what this is going to do is it's going to run the simulation by sort of ignoring this thermodynamic violation. And what we want to do, or usually you don't want to run it this way, but the objective what we want to achieve is we want to have a look at the exact point of where this crossover is going to occur. You're going to get a warning, but not an error, because you already told them you allowed it to happen. So it's going to give you a warning and tell you calculated U, DTLM, and area are unreliable, and you have a temperature crossover. So in order to determine the exact point of the temperature crossover, we're going to plot the temperature versus heat. So at the top here, you see the TQ. Right, I'm going to click on TQ. If you're not seeing this curve for some reason, just go to home, and then you should be able to see it. If it's hiding, just expand this window, you should be able to see it. So if you plot temperature versus duty, and again, let's change the units to similar units. At the top here, I'm changing the units to Celsius, and the duties to kilowatts, okay? And we can see the exact point of crossover, and the purple line here, I don't know, are they both purple? Is this color code pink maybe? So this purple line here is the cold stream, and this pink line is the hot stream. And you can see you have a crossover, at the temperature of 107, and this is your crossover temperature, okay? So at what temp? So question number 5 in the tutorial is asking you at what temperature in degrees Celsius the temperature crossover occur. And when you plot it, you can see exactly the temperature or the point of crossover here. And it's 107 degrees Celsius. Okay, so these results indicate we require a larger flow rate of water to meet the desired butanol outlet temperature. And this is what we did last time. We did design spec to calculate the flow rate of water. We can use the design spec. So, I mean, you can always use a design spec or repeat what we did in the first part to try and determine the flow rate of water to avoid having this crossover. We did a similar one in part 1, right? We did a design spec to determine the flow rate, so we can actually do it in the same way to determine the flow rate in this case. So let's try and run a design spec. Let's first of all go to this heater block, and I want to remove this temperature crossover thing. Okay, so it says under options, conversions, and I want to remove the temperature crossover. And then I'm gonna create a second design spec. So what do we want to achieve in this design spec? It will really be identical to the first one, right? So let's just copy what we did last week. So what we want to do is, I want to duplicate this guy. Can we duplicate an Aspen? It's fine, let's just create it again. It's not a big deal. Okay, let's create a new design spec, and this will be DS2. And in this case, again, I want to define two variables. The first one will be BOH in 2, which is the flow rate in of the hot stream. And this is a stream variable. So let's find it here. Stream variable, the stream we're interested in is BOH in 2. And it's the temperature of the stream. And I want to keep the units as Celsius. So again, I'm defining the two streams, and then I'm defining a second variable here. And this second variable will be H2O out 2, right? So it's the temperature of the water. So it's going to be H2O out 2. And again, this is a stream variable. The stream variable from here. The stream I'm interested in is H2O out 2, and it will be the temperature of the stream in degrees Celsius. Okay. So these are my two variables I selected, or I'm going to use in the design spec. And then the spec I'm going to use, again, it's almost identical to what we did last time. I want the temperature BOH in 2 minus H2O out 2. So the temperature, the inlet of the hot stream minus the outlet of the cool stream, I want this to be 10. And I'm using a tolerance of 0.001. It's exactly what we did last time, except now I'm using the streams for the heat-x model. Okay, so now what am I going to vary? I'm going to vary the flow rate of water, right? So I'm going to vary a stream variable. In this case, it's H2O in 2. And I want to vary the mass flow rate. All right, in kilograms per hour. And again, I'm gonna vary it from 500 to 800. The answer we got last time was somewhere about 697, right? So we should get the same answer. So let's run it and then see what we're gonna get. So let's run this simulation or run this design spec and see what we're gonna get. Okay, we're still getting the same errors because we didn't change the inlet flow rate for X number 2, for heat X number 2. However, now I'm only interested in the design spec. So let's look at the design spec results. As you can see, manipulated 600 final values. So it actually didn't run because it gave us an error immediately. So last time when we ran it, we should get 697. However, this time it stopped running immediately. This could be because we disabled this temperature crossover. So it's not running, it's stopping immediately because of that. So let's allow temperature crossovers and let's run it and see if this will solve this issue with this design spec. Okay. Yeah, so once we allow a temperature crossover under the heatx model, so what I did is under the heatx block, I went to options, I went to conversions, and then I said allow temperature crossover. And this allowed the design spec to run normally and get to 697, which is the exact same result we got last week for the same design spec using the 2 heater models. Ideally, you don't want to allow temperature crossover, so be cognizant of what you're doing when using this model. Okay, if you're playing around with it, when you're running your final simulation or if you're using your final numbers, disable this option of allowing a temperature crossover because these results will not be accurate. Okay, so let's go back to the tutorial. So what's the flow rate in kilograms per hour? It's 697, right? What is the heat duty of the heat exchanger in kilowatts? Okay, so let's go back to the tutorial. And now let's run this heat exchanger using the flow rate we calculated. So the flow rate we calculated actually was 697.607. So I'm gonna go to the heatx. I'm gonna double click at the water inlet. And I will write 697.607. 697.607. And so I change the flow rate of water. And now I still want to remove this allow temperature crossover. I want to run it without it. So let's see what we're going to get. So let's run the simulation. Okay, so now we're not getting any errors. Let's have a look at the stream summary. Let's have a look at the stream results, see if it maintains this 10 degrees Celsius between the streams. So these are temperatures. Let's make them in Celsius. You can see 117, 107. So this 10 degrees Celsius maintained, which is good. And now we need to calculate get the heat duty, right? So I go to thermal results. Heat duty is shown right here at the bottom. Let's have a look at it in kilowatts, and your heat duty is 69.47. And this is the answer to question number 7. Okay, and then you're being asked in the thermal results exchanger details. We can see more information about the heat exchanger, such as log mean temperature difference, 12.3. You can also see the heat transfer coefficient. And the question 8 is asking, what's the required heat exchange area? Again, all of these results are shown here. So after you run it, you should be able to see all of these results. Let's have a look at the exchanger details. And you can see the required heat exchanger area, 6.6 meters squared. The heat transfer coefficient, let's maybe use consistent units that we want to use. It's 0.85 kilowatt per square meters per Kelvin. Your log mean temperature difference 12.3, which is the answer written in the tutorial. Your UA, or your overall heat transfer coefficient, is 5.6 kilojoule per second per Kelvin. So you can get all the parameters for the heat exchanger from Aspen. And again, it uses correlations, so I mean, you can verify them by hand, and you'll see you'll get the same numbers. Okay. So what else do we need to do? Okay, let's have a look here. So in this tutorial, we learned how to model shortcut heat exchangers, all this stuff. Now we will quickly look at the rating and simulation options in calculation mode. Deactivate your design spec and use a water inlet flow rate of 700 kilograms per hour. We're going to do this first, and then the rating option allows us to determine if a specified heat exchanger is over undersized. Go to your heat specification, select rating, calculation mode, leave the hot stream outlet. So this will be the second thing we do. And then the third thing will be leave the hot stream outlet at 40. Okay. Now we have blank options for exchangers. Enter an exchanger area of 8 square meters. Okay, so we want to rate the heat exchanger and see if it's over designed or under designed. Okay, let's follow these steps. So first thing, it's asking us to deactivate your design spec and use a water inlet flow rate of 700 kilograms per hour. So I'm going to go to design spec right here. I'm going to deactivate both of them. So I'll right click on this guy, deactivate, and then right click on this guy as well and deactivate as well. Okay, let me close all these tabs. And it's telling us to use a water inlet flow rate of 700 kilograms per hour. Okay, so I'm going to change this to 700. It's fine. And then the third thing we need to do is go to the HeatX specification tab, select rating and calculation mode. Okay, so I'm going to HeatX specification tab. I can either double click on it here or navigate to it from the left-hand side tree. Just finding my block, HeatX setup. Take us to the same thing. And heat specification tab and select rating and calculation. Okay. Try and find this. Okay, we're in the specification tabs, and under calculation mode, we want to select rating. Okay, so we selected rating. And then we're maintaining hot stream outlet temperature. This is 40. And we want the exchanger area to be 8 square meters or meters squared. Okay, so this is what the problem is asking for. And it's in your in the tutorial or in the document, you're being told that, you know, if you specify this, this is grayed out. If you specify this, this is grayed out because these two are related, use the same equation. So if you specify both of them, you're just over calculating or over specifying your problem. Okay, so this is the case. Let's run this simulation and see what results we're going to get. So it ran, and we really need to find out, is our heat exchanger over designed or under designed? Is 8 meters squared too much or too little? We know it's too much because we already looked at the area, it was 6 point something, right? Anyways, let's go to our thermal results. And under thermal results, let's look at exchanger details. And you can see here that the required exchanger area is 6.5. So when we're using 8, we're over designing by, So question number 9, the tutorial is asking you for the percentage. So 6.58, so 8 minus 6.54 divided by 6.54. So we're over designing our heat exchanger by 22%, right? So it's over designed by 22%, which is the number we have here. And you can use this sort of utility to help gauge, the capacity of your exchanger. And by this, what it means is that technically, if you're at the very initial design stage, you can reduce your area to meet the actual required area so that you maintain or reduce your costs. If you already have the heat exchanger and you're trying to optimize your flow rates, you can see that, I still have 22% capacity, so I could maybe run more fluid through it or use this heat exchanger in a more efficient way. Okay. Then there's the last part here. You're being told, now let's look at the simulation option. The simulation option allows us to determine what the heat duty, let me move to the tutorial, what the heat duty and outlet conditions for the hot and cold streams be for a given exchange area. Okay, in the exchanger opt specifications form, change the exchanger area to 5 square meters, yeah, okay. And we're gonna run the simulation. So again, we're looking at another different mode of running this model in Aspen. So I'm going to double click on HeatX. I'm going to change the calculation mode from rating to simulation. So we looked at design first of all, did rating, and now we're going to look at simulation. And we're going to set the exchanger area to 5. So in this case, I'm telling Aspen to fix the area at 5 and calculate all the temperatures and tell me what the outlet temperature will be if I only have 5 square meters. So let's run it and see the results. So results available. And question 10 in your tutorial is asking, run the simulation, what is the outlet temperature of butanol in degrees Celsius? So this is what we're going to have a look at. We're going to find out, so try and find, so I'm going to look at stream results under the tree here of the HeatX model. And we're looking for the outlet temperature of butanol. So we're looking at butanol out 2, and the outlet temperature we have in this case is 43.34 degrees Celsius. And this is the answer to question number 10. And yeah, this is the end of the tutorial. We're basically looking at the HeatX model, which is the actual representation of the heat exchanger, different calculation modes, how you can use it to size the heat exchanger, how you can use it to run some heat exchanger analysis, etc. Please try to this tutorial. If you're having a hard time, come to office hours, send me an email, and try to learn it. It's a very important skill to have. Thank you very much.